Hello, Hackathon. For the hackathon, I developed a protocol for using post-quantum cryptography in a proof-of-stake system to ensure that the blockchain remains secure even after large quantum computers capable of defeating modern elliptic curve cryptography become available. In Byzantine fault-tolerant consensus protocols like Tendermint, we use a set of cryptographic primitives that, based on the algebra of elliptic curves, that gives us small, compact signatures, and we use those as part of the sort of proof of process for a Byzantine fault-tolerant consensus protocol like Tendermint. In the mid-90s, Peter Shor showed an algorithm that could be executed on future quantum computers that would allow for defeating the security properties of these elliptic curve algorithms. Now, our understanding and our research on quantum computers show that the size of a quantum computer that will be needed to execute Peter Shor's algorithm is enormous. Today, we have very small quantum computers. But increasingly, quantum computing is looking like an engineering problem rather than a physics problem. And as a result, there's a lot of concern in the cryptographic community that large-scale quantum computers might become available in the future. For this reason, we have been developing a set of cryptographic techniques called post-quantum cryptography. Now, post-quantum cryptography comes with a lot of limitations relative, or at least the state of the art of post-quantum cryptography comes with a lot of limitations relative to our current cryptographic techniques that would be vulnerable to Shor's algorithm. Those constraints are primarily that the signatures in the public keys are many times larger than the signatures and public keys that we use today. So if you were to imagine shifting over the Tendermint BFT consensus algorithm to one of these new cryptographic primitives, you would end up with block headers and network traffic orders of magnitude larger than what the current Tendermint protocol, which would make it very slow. And because quantum computers are a problem decades in the future, it makes no sense to apply this. So the protocol that I developed is an incentive system and a verification strategy for including post-quantum signatures in the ledger as the ledger is being built today. So in the future, when and if the consensus protocols of the future need to be upgraded to use hopefully better post-quantum primitives that are available in the future that might be smaller and allow for more compact signatures, the ledger will have the protocol developers of the future will be working from a ledger that they will have complete confidence is the one and only true history of the blockchain. Otherwise, one could imagine a time where potentially quantum computing moves very quickly and it becomes unclear what would be the right transition point and what would be the right history to use, because the entire guarantees of the immutability of the history rest in a proof-of-stake blockchain on the integrity of the underlying cryptographic system.